So now let's start talking about the normal distribution, where the first thing we're going to introduce are a few of the basic properties for what the normal curve is, what it looks like. Where remember, when we talked about distributions back in Chapter 2, we looked at a pattern called the symmetric distribution, where in particular, we looked at it in terms of a shape that is bell curve-like, and that is the type of thing we're talking about with the normal distribution. But for this, we're looking at a continuous distribution. So it's not discrete. It's a little different from what we saw in Chapter 4. There's a little bit more going on because we've got a few more options, more than a few, but it's a matter of scale, I suppose. Where for these, we have that nice bell-shaped pattern in our distribution, and we have that our measures of central tendency, that is, our averages, are approximately equal and in the middle of our distribution, so it reaches up towards that peak in the middle where all of the averages are. The total area underneath a normal distribution curve, because we have this thing as a continuous spectrum, we graph it using a curve rather than just a single value or that string of values like with a discrete thing. That is 1, and when we're finding a probability, we're finding an area underneath the curve. And I'll talk about that more in a couple of minutes here, but for those of you who are calculus literate, what we're performing there is an integral. Hopefully you remember that from whenever you saw calculus, although the type of integral we're doing there is a thing called a Gaussian integral, and that is a integral of special and extreme nastiness, I would say. It's a non-elementary integral. It's not the sort of thing you'd ever do by hand, except for maybe as like a series approximation if you have a Calc 2 professor or a Diffie-Q professor that feels like proving a point. But generally, you don't see how to do that, certainly not technically and in detail, until you spent a long time doing math. Mostly we're going to do this stuff using tables and calculator tricks. But that's the sort of thing we're looking at, where the curve gets infinitely close as you get further and further out, but never actually touches the axes. The x-axis, that is, the horizontal axis, gets so close that it's almost there, but there's always just a tiny, tiny bit of data that's still underneath that curve. And then finally, I ran out of space to write it all out, but the empirical rule holds, because the empirical rule is for approximately normal things, so you can be damn sure it works for the normal distributions, as it were, where, for those of you that don't remember, the empirical rule says that for approximately normal distributions, about 68% of data falls within 1 standard deviation of the mean, about 95% is within 2, and about 99.7 is within 3 towards that middle value. Where that holds nicely when we're talking about the normal distributions and the standard normal in particular that we'll see in a bit. But to help understand what's going on here with these ideas in particular, let's think about things of a distribution flavor. So when we talked about histograms, we had a construction that I didn't spend a whole lot of time on called a relative frequency histogram, where what you do there is you take your classes, and when you're talking about the frequencies, you talk about them in terms of values from 0 to 1. You talk about them as percentages of the whole. So really what you're getting are things like probabilities, where if you have, I'm not drawing in the numbers in here, and I'm skipping on some details about what this represents, fill it in with whatever you think is very important. Maybe it's grades, maybe it's the amount of money you're going to make at different jobs, whatever works for you. Just imagine that's something important. And this is what our relative frequency histogram would look like, where those relative frequencies essentially mean the same thing as probabilities. And if you turn that into a frequency polygon, you get a shape, I did a decent job here, something like this. It's not usually supposed to be quite so triangular, but you get a shape in that flavor. But if you add more classes, if you make these classes smaller and smaller to get more and more specific, well, you get more and more information in here. And this thing would get a bit curvier, and you'd have a better representation when you're talking about this in terms of the area underneath the polygon. And as you get more of a curve, you talk more about an area underneath a curve when you're talking about that whole thing. And if you want to get a probability associated with a group of them, say you wanted to just get whatever the area was in terms of these regions in the middle, which should be about 68%, depending on how nicely I drew that picture. Well, you just find the areas covered underneath that polygon. And that's essentially what's going on here. That's essentially what's going on when we're talking about the area underneath a bell curve, is we're taking those pieces, but we're making so many of them. We're taking these bars for our histogram and making them so very thin, so infinitely thin, that it's like they're just lines. And this curve gets more and more exact, gets more and more of a turn to it. It's not quite so flat anymore. And that type of construction is actually where you get the idea of the integral, for those of you who have taken calculus. That's often how it's taught anyway. But for us, just understand that when we're thinking about areas underneath curves, we're thinking of them sort of in this way, like with relative frequency, that is percentages, that is probabilities. That when we're finding an area underneath a curve in this context, what we're getting is actually just a probability. And next, we're going to see how we can define those probabilities in terms of things I mentioned in the end of the last section with our distribution functions.